All right, so today I have to congratulate all of you. You guys have successfully finished, in effect, the first semester of AB Calculus. So, AB Calculus is over. We're looking in our rearview mirror now at AB Calculus. So here we go. This is the second semester of AB. So we got to start it with a smile here. So, yep.
Super quick question. Do they go deeper in depth or just slower? Okay.
So two fundamental problems that calculus solves. Well, the first semester, or for BC, you know, the first couple of months, we solved the tangent line problem. And how did calculus solve the tangent line problem? Through a derivative. But what is a derivative? It's a limit. That's right. So I'm going to draw my tangent line, my f of x with the tangent line. There it is. And this point is x, f of x. And how did it solve the problem? It said that the slope of the tangent line, or f prime of x, was going to equal the limit as h goes to 0 of f of x plus h minus f of x all over h. So yeah, we solved the tangent line problem. Or I shouldn't say we, calculus solved it. We just got to enjoy the ride. The second part of calculus solves the area problem. You might be asking, how can area be a problem? Right, so here we go. I'm going to give you an example. Let's say, what do we know about area? If I have a function that's f of x equals 4, that's just a horizontal line at 1, 2, 3, 4. Here it is. And I want to say, let's find, we want the area under this curve. From, let's say, -3 to 4. Well, so from -3 to 4, here's -3 and here's 4. 1, 2, 3, 4. And we're going to find the area that's above the x-axis. Well, Mrs. Muller, that's certainly not a problem because it's a rectangle. I know what that is. That's going to be 7. Right, so the area is going to be 7 times 4, or 28 units squared. Certainly not a problem. But then I say, what about if we have this situation? We have f of x equals x squared plus 1. And that's just a parabola. And I want to find the area under this curve from -2 to 2. So how is that a problem? Well, we don't formula for the area under a parabola or a parabolic arch. And the answer is we do, but not until later in this unit. But let's, we don't have a set formula, right? Because the area of a rectangle is length times width. We don't really have a formula for this, do we? So what happens when you have a function and it's curvy? We're going to be very basic at the beginning, okay? So this is the area problem. When it's a shape you know, it's not a problem. But finding the area under a curve and you don't have a formula, that's the problem. And calculus is going to solve that for us. All right, so moving right along. I'm going to make this smaller because I don't know why I made it so big, maybe for your sheet so you could see it better, but I need it all on one page. So let's say we have, this is x squared for you guys to label. This is y equals x squared. And let's say I want to find the area under this curve from 0 to 1. And that's curvy. I don't have a formula for it. But, you know, we might be able to estimate the area under this curve. Right, everybody goes there to a triangle, which is 1/2 base times height. But let me ask you this, is there a shape that's even easier? A rectangle, okay? Now, we could use one rectangle. This really should be, I should have it in a different, but let's do it right. We could use one rectangle. What kind of estimate would that be? Pretty bad, wouldn't it? It would stink. So we could say we have an area estimate here with the green of 1 unit squared, because it would be length 1 times 1. Yep, and we could do better by using another triangle. I mean, not a triangle, but a, let's say we decided to make 2 rectangles.
A little better.
Is that a better estimation?
You guys take off.
You guys are so wise. Okay, so what would that area estimate be? It would be its length, which is 1/2 times its height. Well, what is the height here? It's 1/2 times. Right, so it's going to be 1/4 times 1/2, which is 1/8. So it would be 1/8 is the first one. Well, I should just use blue to match. 1/8 plus, that's going to be 1/2 times 1, which is 1/2, which is going to be, if I put these in eighths, 5/8 units squared. Did I get even better?
Yes. Let's add more.
That's right. Add more rectangles. So let's do that on the next page. You have another graph, I assume.
Yeah.
We have 2 more.
You have 2 more?
We have many graphs.
2 more.
Only 2 more?
Only 2 more.
Okay, well then we need to use the graph that I have here for the very first one. So I'm gonna use now 4 rectangles. So that means I'm gonna start at this height and make a rectangle. I'm gonna start at this height and make a rectangle. And then I'm gonna start at 0.75 and make a rectangle. And start at 1. So this was going to be my area estimate. Is this going to be a better estimate? So now, do all of these have the same width here?
Yes.
1/4. So could I factor that out in front
Yeah.
and then only add up the heights?
Yeah.
Okay, that's good. So this is going to be 1/4 squared,
1/16.
1/16. Plus, this is going to be 1/2 squared,
1/4.
1/4. Plus,
9/16.
This is 3/4 squared, which is 9/16 plus 1. Now you guys are really quick with the calculator and can give me that answer, right?
You want us to like,
I don't want to have to add it up. You want me adding it up with the 89? What do we get?
It's 30/16. So it's 15. 32.
15 over 32? Times 1/4?
No,
No,
that
that
wasn't the one. That's
that is,
including the
that is
one.
Okay.
just the answer.
15 over 32 units squared. So I could say the area is approximately, you notice I put estimate here. I could use the approximately and say 15 over 32 units squared, okay? Now, everybody, I'm sure, can tell me right now if this is an overestimation or an underestimation. Clearly it's over because I have the rectangles that have some stuff above the curve, right?
If you underestimate it, if you went from the
Yep, we're gonna go there. Okay, so where did I choose my heights from in this case? I chose them from
the right side.
the right edge of the top, didn't I? The right vertices. We call this the right rectangular approximation method. Gosh, and that is a lot of letters, isn't it? So this is called RRAM. And it's RRAM because we chose the right edge. Yeah.
If you wanted it to be more accurate, could you alternate whether you chose the right or the
I mean,
left?
yeah, we could, but we're not gonna do that.
Okay. Because then would you just not know?
Yeah. Okay. Could I have chosen the left edge? The left upper vertices? Well, that's what we're gonna do. We're gonna do LRAM. So we have another blank grid here, and we're gonna use 4. We're still finding the area under the curve from 0 to 1. And I'm going to choose the left edge. Well, when I do that, what happens here? The first rectangle has what kind of height? 0, which is okay, because this is just an approximation. And then I choose my height from the left edge here, and then the left edge here, and then the left edge here. And everybody in here can tell me that they believe this is an underestimation. So what would the area estimation be here? Well, what are the widths still? 1/4? Do we agree? And then the height, first height is 0 plus. Then we're going to say 1/4 squared, which is 1/16 plus 3/4 squared, which is 9/16 plus,
And then you need the
and then
no, we need the 1/2.
no, we don't need the 1, do we?
Or the 1/2 though.
Oh, I forgot the 1/2. Let's not do that. That would be bad. 0 plus
1/16
1/16
plus
plus-
1/4.
I'm sorry, 1/4 plus
9/16.
9/16. So I should have 4 representations of heights, right? Because I have 4 rectangles. So somebody give me what this estimate is. Sorry, what? I got 7 over 32. Is that right? Units squared. Clearly this is an underestimation, yes.
What are you getting 9/16?
I'm squaring 3/4 here. Because this curve here is y equals x squared. And when I put my input here of 3/4, the height here is, right? Because this is length, I mean width, and these are the lengths, right?
Gotcha.
Make sense? That's how we're finding the length. So this is length 1, this is width, length 2, length 3, and then length 4. And this is now an underestimation because the rectangles lie below the curve. This one is called, since I used the left edge, LRAM, which is, instead of right rectangular approximation method, it's left. Well, clearly you have one more graph in your notes, so there's one other rectangular approximation we're going to do, and it's going to be MRAM, which we're going to use the middle of the interval. Okay? So let's get ready on our graph here. So I'm still finding the area under the curve from 0 to 1. And now I'm going to choose the middle of the interval as my height. Well, what is the middle interval between 0 and 1/4? 1/8. Good. Okay, so I got that rectangle. Then I go in the middle of this interval and I choose my height. 3/8. Yep. And then 5/8. And then 7/8. So that's where we're going to get our heights from. The middle of the interval. Now, what do we think about this approximation?
It's still an overestimation. Wait, does it bounce out? It looks pretty close. Does it
Well,
bounce out?
we'll find out. I've got
a bigger difference to the right of it.
well, let's
This is
see.
bigger.
So the area estimation is going to equal 1/4, right, which is its width. The width is still the same, right, of the interval?
Yeah.
And now the height's going to be 1/8 squared, 1/64 plus 9/64, 25
40.
64 plus 49/64. And when you do the math, what do you get? 21.
21/64.
So let me ask you this. Of the three, which do you think is going to be the better estimate? M. And this is, yes, indeed, MRAM. Let's draw my M better here. Which means they call it midpoint. Middle, midpoint. Rectangular. Oh, I can't spell. We all know that. Approximation method, or MRAM. Now this has a little bit of overestimation and a little bit of underestimation. Yeah, well, we'll get there. Okay, so may I have the decimal for this? Yes, ma'am.
Why are we always squaring the lengths?
Because this is y equals x squared, and this length here is going to be, this is length 4, right? It's going to be 7/8 squared. Okay. No problem.
0.328.
I'm sorry.
0.328.
0.328. All right, so let's go back, and can you give me the decimal for this one?
0.219.
0.2 what?
19.
And then let's go back one more time and give me the decimal for 15/32.
0.46875.
.469. Oh, yeah, that makes sense.
0.469. And if I were to tell you that the exact area under that curve is 1/3,
Yeah, it's over.
It's under.
MRAM is.
MRAM's pretty close. But how many rectangles? 4. Imagine how much better we could do if we had 6 or 8 or or infinite.
Oh my god.
Oh my gosh. What happens the more and more rectangles
Closer it gets.
closer it gets to the true area. But now where have you heard this language before? The closer and closer it gets. It's a limit. So how many rectangles am I going to approach?
Infinity.
Infinity. Guess what? That is how calculus solves
Area.
the area problem.
Very expensive.
Could we use these in free now?
What?
Could we use this in free now?
All right, here we go. Now we're going to do for generic curve. Well, this is my generic f of x. And so we're going to come up with generic formulas for LRAM, RRAM, and we'll do LRAM first. Now, did we do right first? We did right first, didn't we? So let's do right first. Let's be consistent here. RRAM first. Now, I can use equals here if I'm saying it's an approximation method. Right? If I was saying what the area was, I'd have to use the approximation symbol, the squiggly equals. All right, so here we go. I'm going to try to find the area under f of x from A to B. And if I'm using RRAM, that means I'm using the right upper vertex. So I'm going to use the right upper vertex. I'm going to do the first one. So here it is. There's the first one. And then I'm going to take one here. And I'm going to take one here. Now, in this class, we're going to use varying widths sometimes, and we have to add them up individually. But for this first few lessons, we're going to have the same width. Okay? I'm going to call this width delta x. Now, if I had to come up with an expression for delta x, how would I calculate if I know where I'm starting and where I'm stopping, what delta x might equal?
A minus B divided by
A minus b?
B minus A.
B minus a would be the length of the interval divided by however many rectangles we have, and I'm going to call that n for number of rectangles. Now I'm foreshadowing. I can't spell rectangles. Okay, I'm foreshadowing a little bit, but what happens to the width as I go to infinity with the number of rectangles?
It's so
Almost as if it's a line.
It's approaching.
Right? The width is so narrow, right? Okay. So what would this first value be? The width is going to be delta x, right? So every rectangle is going to have a delta x attached to it, right? What's the first height going to be? It's going to be f of, it's not f of a. Yes, f of a plus delta x. Good. Plus, what's the next height going to be? Oh, yes. F of a plus 2 delta x. Plus, dot, dot, dot. Plus, could you give me the last one?
Yeah.
F of b. Because I use the last height in LRAM, I do. And LRAM, I don't use the first height, I use, I use the second height because I'm using the right edge, and then I always use the last height as my last one. Everybody got that? All right, so what would LRAM be? Delta X times, now I'm going to start with left edge. On my picture, here we go, left edge, here's my first rectangle.
Okay.
I know, hold on, let me draw for the people at home. This is LRAM, I'm using the left vertices, and I'm going to put a dot, dot, dot here, okay? So, the first height I use is f of a, you're right, plus
F of A
plus delta x, good, plus f of a plus 2 delta x, plus dot, 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 plus f of
B minus delta
f, I can't fool you guys, b minus delta x, good. And with LRAM, you don't use the last height. And now we're going to do, I'm trying to think of what would be a nice complement. We'll use gold here. The middle of the range here, or the middle of the interval. This yellow is going to be the MRAM. Using the middle as my height. So the area, MRAM, is going to equal delta x times,
F of A plus 1 delta.
yep, f of a plus, I usually do delta x over 2, but yeah, 1/2 delta x works. Right, plus
F of A plus 3 halves.
3,
3 delta X over 2.
yep. Because they're delta x apart, aren't they? So you're going to add a delta x every time. Plus, I'm going to go to the end. F of b minus
Delta X
delta x over
over 2.
2. Yeah.
After f of a, 3 delta x over 2 would be f of a plus 5.
5 halves, yeah, because what we're doing, we're adding 2 delta x over 2 every time, right? Because we're adding their delta x apart.
Yes.
All right, so that is RRAM, LRAM, and MRAM. Sure. You mean this way? Up here. I'm sorry.
Thank you.
All right, so we're going to do an example on the next screen. And I'm going to actually give a name to these now. They're called Riemann sums. Because the guy named Riemann came up with this method. So if you ever hear of a Riemann sum, what are you doing? You're adding up the areas of rectangles. Okay, so let's, I'm going to do a really basic problem here. We're going to find the area under this curve, negative x plus 6, from negative 6 to negative 4. Negative x plus 6. So I'm going to graph that line. We've got a negative slope. We're going to go from, well, it would help if I made my line actually straight. Not necessarily straight, but I've got at least the points there. Okay, so we're going to find the area from negative 6 to, area under the curve from negative 6 to negative 4. Now, before you guys tell me, oh, Mrs. Molly, that I can figure out the exact area, it's a trapezoid, right? I get that. What is delta x in this case? Remember, delta x was defined as b minus a over n. And they want how many rectangles in this case? 4 left endpoint. So they want, this is an A LRAM with how many rectangles? 4. Sometimes you'll see it as a sub 4. That's a sub of a sub. Okay, so I need 4 rectangles, and my my B is -4, so we're going to say -4 minus a minus. No, try again. -4. I wrote -6, and I meant -4. So this is -4 minus a -6. Right? I go. This is A, and this is B. Oops. All over 4, which is 1/2. So I'm going to use a very thin line here and draw my rectangles. I'm using the left edge. So I'm going to have 2 rectangles per.
How is that left? What's the right and right?
Oh, I did right by accident. Sorry. I'm sick. What can I say?
She was doing right. We're going back to the left.
I'm sorry.
Did it tell us we had to use the left hand?
Yes, it did.
Where did it say that?
It said left end point.
Oh, gotcha.
The good news for me is I don't have to erase. I can just
Undo.
undo. Oh, not that much.
Undo way too much.
Right. All right, so left edge means I'm starting over here and going down. Thank you for correcting me. Actually, it's easier for me to draw those for some reason. Is this an overestimation or an underestimation? Overestimation. Okay, so if I want to say the area estimate is going to be, what is the width? 1/2 times the heights now. That's going to be f of -6 plus f of -5.5. Would you agree? Plus f of -5 plus f of -4.5. No.
Yeah.
Okay. So what is f? F is negative x plus 6. So what's the first height going to be?
0. Wait.
I have a 12. Right?
Oh, yeah.
12 plus, and then when you put 5.5 in, you get 11.5 plus 11 plus 10.5. And if you were to add all those up, you get 45 over 2, which is 22.5 units squared. Now this is then A LRAM with 4 rectangles approximation. So what is the real area? Area of a trapezoid, which is 1/2 the sum of the bases times the height. Well, the bases are, so I'd say 1/2. Well, base 1 is going to be this length here, which we said was 12, plus the height at -4, which was 10.5 times the height, which is going to be.
Wait, what did it
Sorry.
What?
And the base
It's
cube
12
should be
plus 10, not 10.5.
So 10.
What's it? -4. Oh, right. It's 10. You're right. Thank you. Yep. And so this is going to be 22 over 2. Oh, I forgot the height, which is 2.
Height's 2, yeah.
So these cancel.
That's good.
It's 22 units squared. How close were we with
Only 0.5.
25? We only had 4 rectangles. That's pretty good. All right. I'm not going to do the next 2 because I think we can do that. Please tell me I have some notes after this. That would be okay.
Yeah.
I don't. You do. So here we go.
Uh-oh.
If you drive a car, and you have that? When you drive a car and you travel 25 miles per hour, so this is going to be your velocity, and this is your time. This is the biggest application of this. And I'm driving 25 miles per hour. Distance, in this case, is equal to rate times time. Okay, and I'm going to go travel for 3 hours. This is in hours. What happens when I say 25 times 3? You get 75 miles. I've gone 75 miles, which just so happens to be the area under this curve. So the area under the velocity curve turns out to be position. And if it's a positive area, then it's distance traveled. Okay? Questions on that? All right. Oh, maybe I just, oh, there it is. All right, so we're going to do this one really quickly. I'm just going to set it up. All right? Now, we're going to estimate the volume of the sphere.
That's not. Whoa. That's a little.
Okay? Now, the radius is 4, and this function here is
It's a little proud.
square root of 16 minus x squared. Now, what am I adding up here? I'm adding up a bunch of volumes of right circular
Oh.
cylinders. Do you agree?
But cylinder.
So volume of a right circular cylinder is pi r squared h. And it looks like we're using LRAM here. Does everybody agree? No, it's just the way the problem the book is set up. Is there a reason?
Like, how do we know to do that?
They just did use LRAM, but you could have used R.
Okay.
They'll specify.
It looks like it.
It looks like it's over on one
Does
side.
it look like it's RRAM?
No, it looks like it's different on either side.
Okay, well, we have to make a decision. So we're gonna make the decision that it's L. Is that okay?
Sure. Will they
If
specify?
it's L, no, we're not gonna do M. Too complicated. All right, so the volume estimate. What is gonna be the same for each one of these?
The heights of this.
Right, so what is the height? The height is
It's just
delta X, isn't it?
The X.
What is R?
4.
No, well,
Well, it's Y.
it's Y, but what is Y?
6 squared.
So this is Y squared, right?
60 minus x squared.
Right, where Y is equal to the square root of 16 minus X squared. You agree with that?
Yes.
All right, so if I were going to write this out, and could I multiply this by 2?
2.
Yeah.
And just do from 0 to 4? Yeah.
Okay, yeah.
So we're going to go 2 times, and what's common to each one of these cylinders? A pi?
Pi is the same.
Pi is the same, and
Delta X is the same.
delta X is the same. All right, but what is delta X? Delta X is, it looks like it's 1, isn't it? Because I'm adding up 8 of these. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. So delta X is
1.
1. So that's common to all of them. And what's the only thing that's different is Y. Each radius of these are a little bit different. But I'm squaring them.
So 16 minus x
So
squared.
y squared equals
16 minus
16 minus x squared, okay? So
Oh, you're squaring.
in this formula, so I'm going to say that this is going to be y squared of 0. Do you agree with that? That's the first height. I'm starting from 0 going this way. That's the first radius squared. Do you agree?
Mhm.
Plus y squared of delta x is 1, so I'm going to add 1 plus y squared of 2 plus y squared of 3. And that's where I'm stopping. So can somebody with an 89 do this for me? Go to y equals in your calculator and type in 16 minus x squared. Okay? And then and once you do that, you're going to go to the home screen. And then you're going to go 2 pi times parentheses, or you can use brackets, right? Whatever you want to do. Parentheses. And then you're going to go y1 of 0 plus y1 of,
One.
I mean, because y1 is where you stuck your function,
Yeah,
right?
y1 is 0, y1 of 1.
Now, because I have to square in y1, right?
Oh, yeah, wait. It's square each one.
No, you don't, because you already squared it in y equals,
Okay, so
right?
You put y squared into y equals.
you
Yeah.
put 16 minus x squared.
Yeah,
and
into
then
y
put the-
equals, yeah.
Okay, so you don't need to.
So can somebody please do that for me?
100 pi.
What'd you say?
100 pi.
So we get 100 pi units cubed, right? So remember, in y1, what did we put on our calculator? We put in
16.
y squared, right? Which was 16 minus x squared. Okay, so now, what is the actual volume of this sphere of radius 4? We know that the volume is equal to 4/3 pi r cubed, such that r equals 4. What did you get there, Will? It can be 64 times 4. 256 pi over
28.4.
No, but what is it? It's
256 pi over 3.
and you said that's what approximately?
268.083.
Units cubed. 100 pi is going to be what?
314.
314 and change. So this is clearly
Not that great.
an overestimation. Does it make sense that it would be an overestimation? Looking at the picture,
Yeah.
it would be, right? Could you get better? The answer is,
We do add more
In the middle.
delta x's,
well,
do
you
middle.
could use the MRAM approximation, or you could add more
add
right circular
cylinder.
cylinders. Okay. All right, so that's all I have for Riemann sums and adding up and finding areas. Now we're going to do some antiderivatives. Yes.
So are these all AB final projects?
No, not final projects, no. Now I have a program where you can, it adds up Riemann triangle, or Riemann sums that I need to give everybody. So, but I have Monday, Wednesday school today, so I know, it's my favorite thing. Nobody can see my face, right? All right. What we're going to do now is something called derivatives in reverse. We're going to go backwards, okay? So I'm going to skip this part because I think we know how to take all the derivatives, yes? All right. So now we're going to play this game. Well, what is an antiderivative? Well, it is the family of functions that share the same What do you suppose? Same derivative. All right, and so what we're going to do is play the game where I'm going to give you the function I took the derivative of, and you're going to give me what I took the I'm going to give you the derivative, and you're going to tell me what I took the derivative of. I said it backwards. I'm sorry. Okay, now this symbol here is an integral symbol, and you see it in my, my wacky symbol. That means take the antiderivative. It's an operator. Okay, and they call it an integral symbol. INTEGRA, integral symbol. Okay, so this is inside this integral symbol is somebody's derivative. Whose derivative is sine? Negative cosine x. Wow, you've played this game before. Now I'm going to put a plus c here because
You don't know if there was a constant.
I don't know if we could have taken the derivative of negative cosine x plus 7
No.
plus pi. But this is a family of functions, and the only thing that separates them is a constant, right? So it's a family of functions, all right? Whose derivative is 1 over x? Right, but we have to do this when we do this. Natural log absolute value plus c, because you can't take the log of a negative number. All right? Plus c. I affectionately call that c a cupcake because all teenagers love cupcakes. I had only one, Daisy U, who didn't like anything sweet. So we named it, the cupcake became the coolest thing ever that you could think of, right? Okay, whose derivative is cosine? Sine.
Plus C.
Plus c. Oh gosh, e to the x. E to the x plus c. Everybody's favorite one because it's its own. Yes.
What are all the dx's there for?
That's a great question. And what do you think we were doing just a minute ago? We were adding up rectangles, yes? And so this is going to be the length, and this is the width. So antiderivatives actually turn out to be the area under the curve, right? Okay? But I'm not ready to go there yet. We're just going to find the family of functions right now, okay? I'll tie that loose end together, I promise. All right, secant squared's derivative of what? Tangent. So that's going to be tangent x plus c. A to the x. A to the x divided by natural log of a plus c. Now, why am I dividing by the natural log? Because when I take the derivative, you have to multiply. And we're going backwards. So when you go backwards, you end up dividing instead of multiplying. The derivative of a to the x is natural log of a times a to the x. When you go backwards, you have to divide. Because they're opposite operations. Okay, whose derivative is sec tan? This is secant x plus the cupcake. Whose is this derivative? Inverse sine of x plus c, or negative inverse cosine of x plus c, right? Because the cosine inverse's derivative is negative, and a negative times a negative is positive. Next one. Whose derivative is 1 over 1 plus x squared? Inverse tan. Look, you guys are really good at this game. Or, you're right. Negative inverse cotan plus c. Yeah. Uh-oh, whose derivative is cosec cotan? Negative cosecant of x plus c. Good. Uh-oh. Pretend there are absolute value bars there. Secant inverse plus c. Yep, I heard it. Or negative cosecant inverse plus c. Oh, I got 4 minutes. X to the n. X to the n plus 1 over n plus 1 plus c. What happens when you take the derivative of x to the n? Oops, I'm sorry. You go x to the n. You're going to go, this is to the n. Gosh. I'm nervous because I only have a little bit of time. N x to the n minus 1, right? What's the opposite operation? That means I'm going to raise the power 1 and divide by the power. Because we're doing the opposite operation, okay? Cosecant squared. Negative cotan x plus c. This one is negative tan inverse.
Plus C or cotan inverse.
Oh, just cotan, sorry. Everybody follow? Not too bad?
Yeah.
Move right along. Now this is your sheet, your homework sheet. I'm going to do number 1. We're going to find the antiderivative. I'm going to label it capital F for antiderivative. I'm going to raise this power 1 and divide by 3. 3x to the third. If I were to take this derivative, what do you get? Boom. Minus, I'm going to raise the power 1 here, x squared. Divide by 2, and you get, and if you take the derivative of that, you get 4x. Boom. See, it's so nice. You can check your answer. Plus 3x plus cupcake. Yes. And the nice thing is you can take the derivative of that and see if you're right. I'm going to rewrite this as x to the minus 3 minus 3x to the minus 2. So capital F, or the antiderivative, is going to be, I'm going to raise the power 1, x to the negative 2 over negative 2, x to the negative 1, I'm going to put a 3 here, over negative 1. So let's simplify that. That's going to be negative 1 over 2x squared plus 3 over x plus c. And if we were to take the derivative of that, do we get? Yep. Amazing, isn't it? It's going to be x. I'm going to raise the power 1. 9/4. Divided by 9/4 means I'm
4 9s.
multiplying by.
Good afternoon, everyone. Let's prepare for our afternoon announcements, prayer, and dismissal.
X to the 5/4, right?
This was a continuation of the announcement this morning that got cut off. So attention freshmen, if you would be interested in being a student guide for prospective students when they shadow at Blessed Trinity, please attend a brief but mandatory meeting after school on Thursday in the Learning
Now
Commons
let me give you a
at
handout number 7.
2:57. This is for freshmen who would like to
On
be
number
shadowed
7, you need to
by
factor.
prospective students. Thursday,
First.
Learning Commons, 2:57.
Yeah.
Following
And on the
students,
back, all you
please
need to
come to
do
the
is
front
solve for the
office to see
cupcake.
Mrs.
I
Hart,
give enough information to
Agent
solve for the cupcake. Yes,
Avery
sir?
Hernandez, Jessica Sobieski, Brian Adway,
You can if you
William
want. I'm not
Willis,
gonna, that's part of your notes.
Roy Connolly, and Clayton Curran.
Okay.
And if the 5 students who were comprising the student entrepreneur panel at Career Day yesterday, thank you, and would you please come to my office right after dismissal. Please stand for our evening prayer.